So a somewhat new game in town is, so data sets are good for dealing with data that has a structure that's kind of basically rows and columns and things like that. If you want to deal with data that's basically an entity property kind of thing, we have a new thing we call entity store, which is kind of a user level way of having something that is just like the entity property system that we've been creating for a lot of the curated data that we have. And the idea is it's a nice thing using UUIDs and so on to keep things apart and letting you build your own sort of private entity store that you can save in the cloud, or letting you knit together different entity stores and so on. All right, so then, once you have an entity store, you can store it in a public cloud and a private cloud. You can register that entity store so that you can knit it together with all of the other curated data that we have and so on. Well, so I mentioned, I've mentioned data curation a bunch of times, and I've mentioned different kinds of data curation. One of the ones that's been interesting for us is image curation. And that's been important in, for example, our machine learning technology stack. I showed one example earlier of our image identification system. It's something we brought out early last year, actually. There's a consumer website that's based on it. Let's see here. We can just go to imageidentify.com. And this is a consumer site people use to go and, I can probably just drag that in. I can drag in pictures, and it recognizes about 10,000 different kinds of objects. It does a pretty good job now of recognizing even quite specialized types of objects. It was based on about 30 million images used as a training set. And the main, I think our image identifier does rather a lot better than pretty much anybody else's general purpose image identifier. The reason is not particularly the underlying neural net technology, which is sort of standard state-of-the-art technology. It's rather that we did a pretty good job of curating the training set. And again, using the same kind of curation methodology that we've used for numerical, geometric, other kinds of data sets, also being able to curate an image data set, the same kind of methodology. I think what's interesting about curation from the point of view of many organizations is that curation requires kind of judgment at all levels. And the difficulty is, a common difficulty is, how do you, when you're dealing with 30 million images, for example, how do you actually inject, you have to have a combination of automation and human judgment, and how do you inject the right level of judgment at the right level in the process to get something like that done in an efficient way? Well, actually, we just brought out version 11 of our technology stack, and one of the things that's new there is much more sophisticated capabilities in the neural network area, let me try to show you an example. One of the things that is sort of a new frontier of curation for us is curating neural networks themselves and curating models around neural networks. So, for example, there's a notion of a net graph, and a net graph is a neural net graph. And let's take a look. Oh gosh, where is there a good one? Well, this is a very boring neural network graph, but I was looking for a more interesting one. Oh yeah, here we go. So this is a typical neural net graph that contains a series of different operations that are dot plus layers and softmax layers and other kinds of layers that you find in neural networks. And the point is that you can take that, what we've been doing is the machine learning and deep learning and neural nets and so on are one of these areas that I've probably seen a dozen times in my life. It's an area that's in hypergrowth at the present time. When I worked in physics in the late 1970s, particle physics was in hypergrowth at that time. It was fun to see because there was kind of a major new result every 2 weeks or something, which particle physics flatlined sometime in the late 1970s in terms of that type of activity. But the area where that's happening today is in machine learning and neural networks and so on. And so we've sort of committed ourselves to surfing this particular period of hypergrowth where there's interesting new result every 2 weeks. And basically the next curation frontier for us is taking every interesting new neural network that comes out in all the papers that are coming out and curating them in a neural net repository so that we can provide for people the latest neural net that does automatic colorization of black and white movies, or does some kind of thing for generating handwriting or whatever else. And so to do that, we've got this underlying system that represents symbolically the structure of a neural network. It kind of lives on top of the standard things like MXNet and TensorFlow and things like this, and allows you to construct a neural net which will sort of automatically be knitted together in the appropriate way from the symbolic description. So sort of an interesting area of curation, because there's the raw network and then there's a trained network that you have to curate, and then there are features that you get from a trained network. So for example, in image identification, the sort of step 1 is curate the 30 million images. Step 2 is derive feature vectors, derive essentially feature extractors from what, when you look at all those things in the world, you realize that there are certain kinds of features that discriminate between different kinds of objects. And what the system is doing is learning those discriminations. You can then take those discriminations and use them to identify other images. So right now, if you have a specialized image data set, it becomes, because we have this sort of pre-curated collection of feature data that comes from our training of the 30 million images, you can then use those feature extractors to incredibly much more quickly train on some particular data set that you might have of pictures of fishes or car accident results or whatever else. And again, this is sort of an interesting area of curation, because one's got kind of the raw underlying neural network, which has its complicated structure, but hasn't been trained. It has no weights associated with it. Then you've got various trained neural networks. Then you've got the feature extractors from the neural networks, and so on. And the result of that is sort of a new kind of building block for programming, because what we're expecting is going to happen is people will take these neural net building blocks, and usually when you write programs, you think, well, what's the way that this function produces its results, and it will be glued together with this other function. In the case of this type of system, what you would have is something which says, okay, this is a block that sort of understands something about images and classifies them. This is another block that generates natural language. Let's just take those two blocks, put them together, and then train on finding descriptions of images, for example. And this is something that seems to work rather nicely, and where you're taking these sort of curated blocks of functionality from neural networks, and then knitting them together, not by sort of human engineering effort, but by applying training data and so on. Okay, so that's so mentioning another frontier of data and curation. A big project that we've taken on is curating pure mathematical concepts. So there are about 3 million theorems that have been published in the history of mathematics, and we're interested in representing all of the knowledge that corresponds to those theorems. It's a big project. The first step of that project is the notion of something like an entity of, this is a species of animal or something. There's no similar notion for mathematics. It's a bit more complicated than that. Let's see if I can find, let's see. Let me just see if I can find something here. Let's see. Not sure if that's right. That may not be something. No, it doesn't know what that is. Okay, so what I was hoping to show you, but realized that I don't have readily at hand, sorry, so in mathematics, the issue is that one has to kind of curate the underlying concepts of mathematics. We've done a lot of that in Mathematica. We've kind of we've finished the 19th century completely as far as the kinds of concepts that you need for mathematics, and we are now the challenge is to cover the whole 20th century and beyond, so to speak, with all of the mathematical concepts that are needed to represent all those theorems and so on. And what happens is you'll have a concept like a function space, let's say, and you'll have various kinds of elaborate mathematical properties of that and mathematical computations on that. And I think there are about between 1,000 and 1,500 of these kind of mathematical concepts, like, this is asymptotically equal to that, or this is the homotopy of this is that. These are kinds of computational mathematical concepts, and there are probably another 1,000 or 1,500 over and above what we already have in Wolfram language that sort of cover up to the present day of research that's been done in pure mathematics. Once you have those concepts, within each of those concepts, there's then typically a whole bag of kind of just similar entities. So for example, with function spaces, once you have the notion of a function space, then there are 500 different kinds of function spaces that people have studied in the literature of pure mathematics. And so that then becomes a more traditional curation project, although it's one where you're going through textbooks and papers and picking out the features of these things from theorems. So that's a coming attraction, is the effort to curate the facts of pure mathematics. Another coming attraction that is still earlier stage of development is something I've been working on. Its current name is a Symbolic Discourse language. I don't know if that will be the surviving name. But the challenge is the following. So in the Wolfram language, we've been trying to find representations of lots of kinds of knowledge and data in the world. And we've covered many different areas. But there are plenty of things in kind of everyday language and so on that we've not covered. If we say, I want a piece of chocolate. Okay, we have a pretty good representation of a piece of chocolate. We don't have a great representation for the I want part of that sentence. So the question is, can we have a precise representation for sort of everyday discourse? And the answer is definitely yes. One can start thinking about it in terms of nouns and verbs and things like that, but actually what's really at stake there is sort of the underlying semantic concepts. Okay, so I've been interested in building something like that for many decades now, and I haven't really had a concrete enough use case to understand what to do. And I think now what I've finally understood is that things like smart contracts, where you're trying to take, for example, just as we're trying to take mathematical theorems and represent them in a precise symbolic way, we would like to take legal documents and represent the content of a contract, for example, in a precise symbolic way. And that becomes pretty interesting because you can then do things like automatically determine whether the contract has been satisfied, things like this. But the challenge first is to curate kind of the concepts of everyday discourse in such a way that you can actually represent that. And so that's something which is an ongoing effort of mine. It's sort of an interesting area because it's something where people tried to do this in the 1600s. Leibniz, when he was kind of inventing some of the things that became sort of our modern notions of computation. His original idea was to take legal documents and find a precise symbolic representation using logic for those kinds of things. And there hasn't been that much work done on this. It's kind of interesting to see what people did in the 1600s. I think the world has changed a bit since the 1600s, and that's reflected in the different kinds of concepts that are important today. Well, anyway, so that's another kind of frontier of data, as far as I'm concerned, is curating the concepts of everyday discourse for the purpose of creating things like smart contracts, or more generally, in sort of the emerging world of AI, there's the question of, okay, so how do you tell the AIs what you want them to do? And for that, you basically need to be able to represent all sorts of all sorts of human things. Another curation effort, which we haven't done, is curating the various kinds of ethical and moral codes of the world. I've sort of decided that that's not as purposeful a project as one might think, but it's something which we will actually be able to do in a meaningful way once we have this symbolic discourse language. The thing that's interesting when it comes to thinking about making computable things like contracts is, one thing is to represent what the contract says. Another thing is to figure out how you get the facts that determine whether the contract has been satisfied. And in kind of the world of Internet of Things and machine learning and so on, there are a lot of interesting sources for that. You know, is this a grade A peach or something? Well, there are a bunch of criteria that are written down for that. But you can make a machine learning classifier that will take an image of the thing and with very good precision figure out, you know, is this in fact something which satisfies the criteria for being a grade A peach or whatever. And so you can expect to have something where the input is coming from IoT, for example, going through machine learning, going into the symbolic discourse language, and then being executed or interpreted automatically. So that sort of brings up yet another form of curation, which is the curation of APIs and services and so on. And so, for example, one thing we've been actively doing is curating different kinds of external services. So whether it's curating access to open library or archive, or for example, Wikipedia is an easy one. You know, you can say, I don't know, let's say, let's get this will just by default get the Wikipedia article on data, just for fun. I'm curious what happens if you do if I just take Wikipedia article for data and make a word cloud out of it. Okay, not too surprising. So another activity is curating APIs. Part of that is dealing with the horrors of authentication for different kinds of APIs. I think we now have a pretty nice symbolic representation of all different forms of funky OAuth authentication that people use and so on. But another is being able to take the kinds of things that these APIs produce and interpret them in terms of our language. And we've been doing a lot on that. Something that is a new thing for us is what we call integrated services, where we're taking something like, for example, satellite image data, which a lot of our customers are interested in, and being able to get data from external service providers, running it through our cloud, dealing with billing kinds of things on behalf of the original data provider, but providing it as an integrated part of our language from a variety of different external data providers. And that's kind of a new thing for us is these integrated services where we're handling kind of the distribution of, in many cases, what I think is going to end up happening is people who have data that they have been providing for some particular market, we provide a mechanism for developers and, in a sense, research consumers and things like that to get easy access to that data in a way where we're handling all of the kind of bureaucracy of what has to happen and letting that data flow directly into our infrastructure and language and so on. So that's kind of a new thing for us. Well, back to more traditional data. Okay, I want to mention something that we are soon going to be rolling out, which is a new thing for us, is our data repository. And the idea is to finally make a data repository that really conveniently works for people. It's the notion is that well, you know, we can take a look here. This has been populated with some kinds of things, you know, whatever it is. It's I don't know. We could go and look at. Let's go back here. Let's say you go here, and let's say, I don't know, that one sounds fun. So this is data from NASA, I guess, on fireballs and bolides observed. So now we can just take this resource, and we can go into Wolfram language, and we can say, let's use that resource. So that will come in like this. We can say, give us, we could say, show the metadata of this, so we can show the sort of default data from here. And this will come in if the, okay, there we go. And so this now comes in as one of our data sets. And we could, for example, let's say we take that, all comma coordinates. Oops. And so now we'll get a bunch of these coordinates. And now let's say, so what happens if I do this? Okay, so that's now showing, taking those geo-coordinates, which have now been, the original data set that this came from probably had these just in plain text. These have now been turned into our geo-position objects, and then the whole thing can flow through this pipeline to come in and get computations done on it. So the idea of our data repository, it's anybody can, within Wolfram language, you can create a resource object. A resource object is something that contains both actual content and metadata and you can take that resource object and deploy it privately to the cloud. You could take that resource object and make it a public cloud object. We could say cloud deploy that resource object to the cloud and give it public permissions, for example. That would allow anybody to access that resource object in the cloud, but they would end up having, I mean, if I just take an arbitrary, let's just take that plot, line 101, and deploy just that particular plot to the cloud, and it will come out as this thing with this UUID. I could go to the cloud. There, it just came up as a web page. This could be an active thing, or it could be an API, or whatever else. I just, in this particular case, just deployed that picture to the cloud. So anybody can deploy a resource object to the cloud for use by themselves or by people that they specify can use it. You can do the same thing in a private cloud, but you can also say, within the language, you can say resource submit that resource object to us for use in the public data repository. Okay, so again, it's all operating within our language. Resource submit is something that initiates essentially a human process of curation, and it will work kind of like an app store or anything of that type, where we will be curating these things. We'll also probably have an open access publishing mechanism, and then those things that are accepted will show up with a kind of a shingle here on in the data repository website, and be searchable and exposed to the web and so on. I think we can go and look at, and there's all sorts of different kinds of data you can put here, because this is just, all the data here is just Wolfram language. It's just represented in the Wolfram language. It can be images. It could be, let's see, what is this? This is it can be text. This is whatever this is. Okay, presidential nomination acceptance speeches. Okay, we could, for example, take that as line 104. I'm now curious, and let's take all of those and say their locations, and hopefully those locations will have been. Let's see whether we can make a plot. So that works. Okay, there we go. So the idea is you can put any kind of data into this data repository and have it be able to flow through our pipeline. So one thing that one thing that's The underlying framework, this underlying symbolic resource system framework, is actually something that can be used not just for data, it can be used for other kinds of things. I mentioned neural net repository, that's another thing that's coming, a repository of 3D parametric objects, repository of APIs, all these kinds of things work using this same resource object framework. And it's easy then to deploy apps and things that call things in this resource system. Well, I thought I would mention just sort of one thing that I've been realizing recently is kind of the general data pipeline. In our kind of world, the first step is you've got to have, the data has got to be somewhere. So for example, you might say, here's a piece of data that's sitting in some CSV file somewhere on the web. And the first thing you can do is just say, okay, let's read that data in. I don't know how big this is, but let's just, I don't know how long, maybe this is a slow network connection. Shouldn't take that long. Okay, so this is just raw reading the thing from a CSV file. Now, within this data, this is data about some kinds of species and weights and lifespans and all sorts of other things of species. And when you just read it in from a CSV file, you'll just get a bunch of maybe numbers, maybe strings, things that happen to be standard in a CSV file. Let's just take the first 5 of those, for example. Okay, so that's a big messy thing with, that seems to be the header of the CSV file, and then there's various, okay, -999, I'm guessing is a missing data indicator, and there's a 39.5, which is probably the weight of some kind of bird, I would guess, based on the fact that it says Aves there. But so this is what you kind of get by doing sort of a raw import of this data. You can also do semantic import of this data, and that's using our natural language understanding stack to try to figure out, given that it's seeing a column and it knows, and it can see, for example, that some things in that column are places, it will then try and interpret everything in the column as places, and will do a decent job of that. And it gets kind of messy to go, we can go and do computations directly on this, but it's kind of messy. So the next sort of step in this is to get the data kind of imported to the point where it is reasonable, where you can put it in a data repository, which means that it's been sort of understood semantically and so on. And so here's a version of this same data set that was cleaned up enough to make it into the data repository. And now we can see, okay, this is now one of our data sets, and it's got female maturity, whatever, in rather overly precise, I would say. I doubt that the bird matures in, or whatever that is, matures in exactly that amount of time. But in any case, that's what came from the data. This is now something which has been canonicalized to the point where we could go ahead and say, pick out this adult body mass or whatever it is, and we could take that and start making histograms of it and so on. So sort of the next step is, the first step is kind of the raw CSV file, reading that in. The next step is sort of semantic interpretation of that, straightening out what kinds of entities these are and so on, putting this in the data repository so that it's possible to access it in a simple way like this. Kind of the next step is to turn the things that are in there into entities, and to make this, there's a version of this where I think that's been done, where this is now set up, great, well, maybe not, where this should have been set up. What's that? Say again? Oh, okay. Well, that's always bad. If it had the wrong name, it's absolutely hopeless. Okay. All right, let's try one more thing here. Okay, that worked. Let's see what happens if I say resource data of that. Okay, so this is an entity store. I mentioned entity stores before, and we can go ahead and say, let's just prepend this entity store to the list of all entity stores. And now what should happen is that we should be able to look for entities that are part of this, that came from this external data, we can treat those entities just like we can treat entities from that are in our internal curated data. So let's see whether that has, yeah. So that's sort of the next step, is to take this thing that was originally a data set and turn it into an entity store where we've identified entities and we've kind of knitted together properties of those entities and so on. So the next step, for us at least, is to take that entity store and turn it into something that would be good for Wolfram Alpha, so to speak. And so that requires doing a lot of linguistics on the front end to be able to access aspects of that entity store, and also being able to do computations on the entity store to generate output that's of interest from that. And each one of these steps, so the first few steps here are quite quick. I mean, matter of, for a typical not totally messy thing, this is a matter of, I don't know, maybe an hour, a couple of hours, maybe as little as 15 minutes to get to the data set stage using semantic import. Maybe if the original data isn't too messy, that might take 15 minutes. To get it into an entity store, maybe it'd take an hour or two, depending on how well structured the data is and so on. To get it to the Wolfram Alpha stage is significantly more work, because the linguistic curation step tends to require a lot of human effort. The kind of setting it up within the Wolfram Alpha framework takes a lot more effort once dealing with weeks to an up of time there. And then the final level for us is getting the thing into Wolfram language as sort of a standard part of our technology stack. That's, as we've realized, even much more work, because what's good enough for Wolfram Alpha for sort of drive-by use of something is there's a lot of, you don't have to have the same level of sort of perfect consistency that you need to have if you're really going to be building significant sort of stacks of computation on top of the data that you put in. And so that's kind of the ultimate kind of platinum level kind of use of data, is to get it fully integrated into Wolfram language. And that's what we've done across a couple of thousand domains of data now. But it kind of gives you a sense that there are these different steps from the sort of the raw CSV file up through the semantically interpreted data set, the thing in the data repository, the entity store version of that, to then Wolfram Alpha version, and then finally the Wolfram language version of that. So it's a lot of work to get it all the way through. It's already very useful, even at much lower levels. So for example, for the data repository, I think one of the things I'm interested in there is supporting kind of data-backed publication of, for example, research data. I mean, there's been a mandate from in the US and other countries for government-funded research to have data that is somehow accessible to the world. The reality is, whenever I actually click on those links that are referenced by a paper, it doesn't actually work. In fact, I think I have not seen a single case where I've actually been able to usefully use the data that's come out from some study or something. So our goal is to make it so that one can actually have that usefully work through our data repository and through the kind of through the sort of both automated semantic import mechanisms and the curation that can be done there. So one of the things that, to support data-backed publication, one of the things that we're doing, let me see if I can do this. Well, here, I can do that. Is from within our cloud, when you take a, let's go here. Oh gosh. So if you create a notebook within our cloud and you say, I'm going to have something that is, I don't know, a plot of, let's make just a table of prime numbers or something here. I got a table of 100 primes or something, and now let's make a list plot of those. Not very exciting, but now if I say I want to deploy that result, and I deploy that, and I say give it a source link, and give it an automatic source link. okay? So that will now deploy this particular thing, and it'll come out as some page here that just has, oh, that's because I'm the owner of the thing. Okay, it would have looked a little different if somebody other than me had been looking at this, because I would no longer be the owner there. Let's get rid of those sample tigers that I was using for image identification. So what you'll see down here, and it would also appear if this was an embedded graphic inside a paper or something, you'll see this thing that says source notebook. And so you can go to that source notebook to go and find where did that plot come from? And so then you'll go to an active notebook where you can recreate the plot. And so a typical pipeline would be, there's data in the data repository. The data in the data repository is taken and turned into some cool visualization, for example, within a notebook. Then that visualization is deployed to the cloud, to the web, as just a picture, but it has a source link associated with it. When you click that source link, you go to the notebook that shows how that visualization was created, and that notebook then references an item in the data repository that gives you the underlying data. And so that way you can reproduce. You can say, that picture in this paper, I can actually reproduce that for myself using that notebook that I found from the source link. So I think this is an interesting, really, really useful, I would have used it a zillion times if papers had come with those kinds of source links that actually allow one to reproduce the results in the paper. So it's sort of a true version of open data where it's not just, here's a blob of data, it's rather, here's actually data that one can guarantee to be able to use, because right here is an actual use of it that you can actually just run in the cloud. Well, there are many, many uses for all this kind of data. One thing that's been interesting recently for us is, on the one hand, we've had lots of sophisticated organizations, from the Silicon Valley startups to very large companies and so on, using our knowledge-based language to build all sorts of interesting things. Kind of the other end of the spectrum is people who are just starting to learn about computation, programming, computational thinking. We've got quite a big initiative going in teaching computational thinking to kids using our technology stack. And it's sort of a unique moment, because people talk about teaching coding and programming. Coding and programming is sort of specialized engineering activity where you're learning how to specifically tell computers how to do particular things. And it's not very well connected to random other things that kids learn in their history class or geography class or language arts class or whatever else. With our language and with all the data and knowledge that's in the language, we can really connect we can really actually focus on computational thinking rather than on the mechanics of coding, and we can bring in all these kinds of knowledge that the kids are learning about elsewhere. And so it's been sort of an interesting process to figure out, how do you teach computational thinking to kids? And it's kind of analogous to the thing that everybody kind of knows is important, which is teaching mathematical thinking and the whole kind of STEM and mathematics direction. There's been 1,000 years to figure out how to teach mathematical thinking to kids. We're kind of at year 0 for teaching computational thinking to kids. And I've been personally quite interested in what the best way to do it is. I wrote this book, which this is a book that seems to be getting used a bunch by adults, but I kind of wrote it mostly for kids. It's a book for that assumes no knowledge of programming and no knowledge of math, basically, and gets to the point where you can deploy cool web apps and so on that make use of serious computation. That book is available free on the web, and there's a thing called Wolfram Programming Lab, which is kind of a wrapper around that book and other activities intended for sort of self-service learning of computational thinking. But the thing that's interesting there is just seeing all of this knowledge-based programming, knowledge-based computation that we put so much effort into and that has become widely used in kind of the research and development community, also being sort of automated to the point where it's readily accessible to kids. And I think it's a pretty interesting thing, because it really, what we see in practice is kind of a very diverse collection of teachers and kids who are not necessarily the geekiest, most technical, most mathy or whatever, becoming attracted to kind of this kind of knowledge-based computation and computational thinking. And I think that's a fairly interesting direction and a really interesting place for this to go. I'll just show you one amusing example. This is a person who was 11 when she contacted us. I think she's now much older at age 12, but this is a post from a kid who lives in New York about using Wolfram language to look at open data provided by New York City about, I think this is about car accidents, which I find amusing because she's several years from being able to drive. That's what does she have here? But what's interesting here, this is just simple Wolfram language code as written by a 12-year-old to go and take New York City data and do things with it. And it's kind of cool that this type of thing is possible for kids to do at this point. And it's kind of a nice place to see kind of the data that a lot of us are putting so much effort into curating and so on, being made available to the future generation, so to speak. Well, it's this whole direction of computational thinking. Part of the reason I think that computational thinking is such an important thing in the world is because sort of all these different fields are moving in a computational direction. And kind of my statement about kind of the future of a lot of intellectual kinds of things is think about all the different fields that people study, from archaeology to zoology. And then imagine that field is called X. And then prepend the word computational to the name of that field. So you have computational archaeology through computational zoology. And the interesting thing is that either computational X for every X already exists, or it's going to exist. And pretty much every one of those computational X things is defining the future of the field, of the field X, so to speak. And I think that's, to me, that's kind of the most interesting thing that's happening as a result of all the work that we're doing on data and curating data and so on, is enabling these computational X for all X. And one of the things we're doing to sort of think about the things that we do is doing more and more with all the different kinds of computational X's. And in fact, when we look at this conference, for example, one of the things I find interesting is sort of picking out the things that are the precursors of computational X that we're seeing in different kinds of data that people are working with and so on. And actually, I think in the future of this conference, we're definitely going to be going in that direction, emphasizing sort of computational X for all X, and sort of emphasizing very much the content of data that we're working with and the purpose of getting that data as a way to enable new fields to arise that are the sort of computational analogs of all existing fields. And so for me, this kind of general approach of computational thinking, this availability of knowledge-based computation, it's enabling these new directions, which I think are really important for both the intellectual world and the practical world going forward. And I think I should stop there. So thank you very much.